Hello children and welcome to my channel Chemistry by Miss Nidhi Banga. Today's topic is all the reasoning or conceptual questions from the chapter Alcohols, Phenols and Ethers. So let's get started. So our first question is, why is the COH bond angle in alcohols slightly less than the tetrahedral angle, whereas the COC bond angle in ether is slightly greater? Okay, so your typical tetrahedral angle is 109 degree 28 minutes. In case of alcohol, the angle is reduced to 108.9. Why? Because of the lone pair repulsion on the oxygen atom. Okay, this lone pair repulsion is greater than bond pair or even lone pair bond pair repulsion. So as they are repelling, they are pushing these bonds a little closer together. Therefore, the bond angle is reduced to 108.9. When we talk about ethers, there is the same lone pair repulsion, right? But there is two bulky groups present here. Now these two bulky groups will also repel and their repulsion would be actually even greater. So they will push these bond pairs away from each other and therefore the bond angle becomes greater than 109.28, which is the typical tetrahedral angle. Okay, so our next question is, CO bond length in phenol is less than that in methanol. Explain. So this is your phenol and this is your methanol. So this bond length, this CO bond length is shorter in phenol as compared to this bond length, carbon-oxygen bond length in methanol. Why is that? It's because oxygen has these two lone pairs and in phenol, these lone pairs are in conjugation with the double bond in the benzene ring. This conjugation makes it possible for these electrons to get delocalized over the benzene ring. When that happens, this bond, the CO bond, acquires a partial double bond character. A partial double bond character. This double bond character makes this bond shorter and stronger. Okay, so if the question is why CO bond in phenol is stronger than that in methanol, then also your answer would remain the same. Because of the partial double bond character, the bond becomes shorter and stronger. Okay. Okay, so our next question is, explain the acidic character in phenol. Phenol is this structure. There is this OH bond. Oxygen is electronegative, hydrogen is not. So oxygen gains a partial negative charge and hydrogen gains a partial positive charge because it's pulling these electrons, the shared pair of electrons, towards itself. Okay, now acidic character of phenol can be explained in many ways. First is that any factor which increases the polarity of this OH bond increases the acidic character of phenol, because more polar bond means it's easy for the proton to leave. Okay, so this benzene ring here is electron withdrawing group. It withdraws the electron density from oxygen, which further withdraws the electron density from the OH bond, making this OH bond more polar and therefore more acidic. Okay, that is one reason. The same thing can be explained as this carbon. If this carbon is sp2 hybridized, this carbon is more electronegative. Therefore, it pulls the electron density from CO bond, making oxygen pull the electron density from OH bond, therefore making the OH bond more polar. There's another way to explain the acidic character of phenol, which is this. So, alcohol, when loses the proton to form, phenol, when loses the proton to form phenoxide ion, this phenoxide ion is more stable as compared to phenol. If the product is more stable, the reaction goes forward. Okay. Now, why is phenoxide more stable than phenol? These are both resonance stabilized, but the resonance structures of phenoxide makes it much more stable than the resonance structures of phenol. How? Let's see. So these are the resonance structures of phenol. As you can see, here there is a charge separation, positive and negative charge separation in 3 of the 5 resonating structures. Charge separation is something that causes instability. Okay. Another thing which causes instability is when an electronegative atom attains a positive charge, which happens here. See, oxygen is electronegative and it gets a positive charge. which makes these three resonating structures contribute less to the overall stability of phenol. But when we see the resonating structures of phenoxide, there is no separation of charges, and oxygen, the electronegative atom here, also does not get positive charge. So these structures contribute more to the stability of phenoxide ion. Whereas in case of phenol, there are resonating structures, but they do not contribute much to the stability. Therefore, phenol is resonance stabilized, but less so than phenoxide ion. And when the product is more stable, the reaction goes forward. Okay, so our next question is, arrange water, ethanol, phenol, and paranitrophenol in increasing order of acidity and give reasons for your answer. So increasing order means going from least acidic to most acidic. And this is the order. Let's see why. We just talked about the polarity of OH bond and how anything that increases the polarity of OH bond would increase the acidity, and anything that decreases the polarity of OH bond would decrease the acidity. So here, let's first compare these two. In ethanol and water, ethanol here is the alkyl group. Alkyl groups are electron releasing group. So they would give electron density to partially negative oxygen atom. Now, if it gets electron density from here, it's not going to pull the electron density from the OH bond, making the OH bond less polar. Okay, so making OH bond less polar means now this is less acidic. When talking about water, in water there is no electron releasing group, so water would obviously be more acidic than ethanol. Now talking about phenol and paranitrophenol, we just saw that phenol is acidic. Why? Because here the OH bond is attached to electron withdrawing group, and which increases the polarity of OH bond, therefore making it acidic. And here, apart from the electron withdrawing phenyl group, there is another electron withdrawing group at para position which further increases the polarity of OH bond. It pulls the electron from oxygen, which further pulls the electron from OH bond, making all the electron density go towards oxygen, and hydrogen is deprived of electron density, which basically means that OH bond becomes more polar. Moving on to the next question. Explain why alcohols and ethers of comparable molecular mass have different boiling points. So these are your alcohol, ethanol molecules. Now here in ethanol, you would see that this is partially negative, this is partially positive, partially negative, partially positive, partially negative, partially positive. So there's a possibility of hydrogen bond here. Okay, so that makes this intermolecular force between the ethanol is very strong hydrogen bonding. Okay, which makes these ethanol molecules come close together, and therefore more energy would be required to break these interactions and pull them apart. When we talk about ethers here, ether is polar. There's a difference in electronegativity between carbon and oxygen. So yes, ethers are polar, but there is no possibility of hydrogen bonding between ether molecules. Because oxygen here is partially negative, but the hydrogens in the methyl group are not partially positive. So they will not make hydrogen bonding with oxygen. So the intermolecular force here is dipole-dipole interaction, which is weaker, much weaker than hydrogen bonding. Okay, that is why there is a great difference between the boiling point of alcohols and ethers. Coming on to the next question. Compare the solubility of ethers and alcohols in water. Now we just saw that the boiling point of alcohol and ether vary greatly, but when we talk about solubility of ether in alcohol, it's actually comparable. Alcohols are definitely more soluble in water as compared to ethers, but the difference is not as great. We'll see how. So this is ether. I just told you that this bond is polar. That means this oxygen is partially negative and this carbon is partially positive. In case of water, there is partially negative and partial positive. So there is a possibility of hydrogen bonding in ethers, okay, which makes ether soluble in water. But let's see how hydrogen bonding is greater in case of alcohols. In case of alcohols, there is a possibility of hydrogen bond between partially negative oxygen of alcohol and partially positive hydrogen of water, and then this partially positive hydrogen in alcohol also forms a hydrogen bond with partially negative oxygen in water. So there is more hydrogen bonding in alcohol as compared to in ether. But overall, there is hydrogen bonding in both cases. Therefore, they are both soluble in water, alcohol more so than ether. Okay, next question. Explain why carbon dioxide is nonpolar whereas ether ROR is polar. Okay, when we talk about carbon dioxide, the hybridization is sp and the shape is linear. This carbon-oxygen bond is polar because oxygen is more electronegative than carbon, but then this is also polar and their direction is opposite. Therefore, they cancel out each other. Therefore, overall carbon dioxide is nonpolar. Okay, even though carbon-oxygen bond is polar, because of the shape of the molecule, overall carbon dioxide becomes nonpolar. When we talk about ethers, ether shape is bent, much like water. So here, yes, this CO bond is polar, this CO bond is also polar, and there is polarity because of lone pairs also. So overall, the resultant dipole moment is significant. Okay, that is why ROR is polar. Talking about the next question. Show how will you synthesize the following alcohol by reaction with suitable Grignard reagent and HCHO, that is your methanol. Okay, so this is the compound that you have to form. Now, let's look at the general reaction that would make it much easier to understand. RMGX, when reacts with methanol, R being partially negative and this carbonyl carbon being partially positive, R will attack here. The mobile set of electrons would move on to the oxygen and you would get this, okay, which upon hydrolysis will give you alcohol. So as you can see from this reaction, the CH in alcohol, the carbon that is bonded to the OH in alcohol comes from methanol and rest of it comes from the Grignard reagent. So now you can form the structure of R in Grignard reagent. It has to be isopropyl group. When attached with MgX forms RMGX, the required RMGX. Now this is partially negative, partially positive. This would attack the carbonyl carbon. The mobile set of electrons would move on to the oxygen and it would form the required compound. Moving on, in Kolbe's reaction, instead of phenol, phenoxide ion is treated with carbon dioxide Y. So this is your Kolbe's reaction to make salicylic acid. Okay, now here the electrophile is carbon dioxide. We just saw that carbon dioxide is nonpolar. It's a nonpolar molecule. Since it's a nonpolar molecule, it's not very good electrophile. It's a weak electrophile. Okay, if this is weak electrophile, if this is weak, we have to make sure that this is even stronger. For that, we convert phenol to phenoxide ion, because the phenoxide ion increases the electron density on the benzene ring much more than that present in case of phenol. Okay, so here this is more activated. So therefore, even a weak electrophile would do the job. Next question. Acid catalyzed dehydration of tertiary butanol is faster than that of N-butanol. Give reasons. So this is your tertiary butanol. When it gets protonated, okay, an important point here, whenever you are showing the attack of a positive species, make sure that you show the arrow going from the electron to H+, because it's the electrons that travel, never the other way around. Okay, we understand that you mean to say that H+ is attacking here. That is fine, but H+ doesn't travel. The electrons move. So we have to show the arrow going from electron to H+. Now after this alcohol gets protonated, the reaction proceeds through SN1 mechanism. That means this bond will break, releasing water and making a carbocation. And we know that tertiary carbocation is much more stable than primary carbocation, which would be formed in case of N-butanol. So since this is stable, this reaction would go faster. Okay, moving on. Why are phenols more acidic than alcohols? Give two reactions to show that phenols are acidic in nature. So this is your alcohol, this is your phenol. This bond is polar. Anything that increases the polarity of this bond increases the acidity. In case of aliphatic alcohols, this is electron releasing group, which decreases the polarity of OH bond, making it less acidic. In phenol, the opposite happens. This is electron withdrawing group, which increases the polarity of OH bond, therefore increases the acidic character. Now, how would you show the two reactions? Now, phenol, okay, before that, the second way to show that phenol is more acidic is that when phenol loses a proton and results in formation of phenoxide ion, which is the product, is more stable than the reactant. Therefore, reaction goes forward. We have already discussed why phenoxide ion is more stable than phenol. How would you show that phenol is acidic? Now, we learned in grade 10 that acids, when react with metal, they release hydrogen gas. So if phenol reacts with sodium, it would also release hydrogen gas. Therefore, it shows that phenol is acidic. We can also make phenol react with NaOH. And if anything reacts with a base to give salt and water, it means that that thing is acidic. Okay, because acids react with base to form salt and water. So since phenol reacts with base to form salt and water, it proves that phenol has acidic character. Next question. Explain why dehydration of alcohol is always carried out with concentrated sulfuric acid and not with HCl and HNO3. Simply because these two would not result in the desired product. Why? We have studied in haloalkane and haloarenes that one way to form haloalkane is to treat alcohols with acid. So when alcohol treated with HCl, it would result in the formation of chloroalkane. Okay, so obviously this will not dehydrate the alcohol, so this HCl cannot be used. We also know that nitric acid is a very strong oxidizing agent. So when treated with alcohol, it would give you corresponding carboxylic acid. So if you are dealing with ethanol, treating it with nitric acid will give you ethanoic acid. Okay, next up we have arrange the following compounds in increasing order of the property indicated against each. Give reasons for your answer. So first is ethanol, fluorine substituted ethanol, and then chlorine substituted ethanol. We have to compare the acidic strength. Acidic strength, anything that increases the polarity of OH bond increases the acidic strength. Fluorine being an electronegative element would increase the polarity of OH bond. Therefore, the order would be like this. But you have to show the order in increasing order. So basically, you would show it like ethanol. Then there is this chloro-substituted ethanol. And then there is fluorine-substituted ethanol. Okay, trifluoroethanol. Moving on to the next question. Next property. 2-methyl-2-propanol, 1-butanol, and 2-butanol. Reactivity towards sodium. Reactivity towards sodium is a fancy way of saying that we need to know the acidic strength. Okay, because this reaction shows the acidic strength of alcohol. Okay, now we know that anything that increases the polarity of OH bond would increase the acidic strength, and anything that decreases the polarity of OH bond decreases the acidic strength. So now let's see. We have this tertiary alcohol here. Now tertiary alcohol, we know that these groups are electron donating. So they would donate electrons, which would donate electron to the OH bond, making OH bond less polar. Here it's secondary. So the electron donating groups are fewer. Okay, so the decrease in polarity would be less than this. And then butanol and butanol. Here there is only one electron donating group. So the decrease in polarity would be even less. So that means this is more acidic, this is less acidic, and this is least acidic. So tertiary alcohols are least acidic, then secondary, then primary. So increasing order would be this. Next up, Unlike phenols, alcohols are easily protonated. Yes, alcohols are easily protonated because alcohols have the lone pair to grab the H plus. Okay, in case of phenols, these lone pairs are involved in they get delocalized over the benzene ring, these lone pairs. Why? Because here lone pair is in conjugation with the double bond in benzene ring. So these are occupied, not available to grab the proton and therefore get protonated. Cumene is a better starting material for preparation of phenol. So this is the reaction. As we can see in this reaction, the byproduct is acetone, which is commercially an important product. Okay, so through this reaction, we also get a commercially important, industrially important byproduct. And other thing is that oxygen is comparatively a cheap reagent. Moving on. In the process of wine making, ripened grapes are crushed so that sugar and enzyme should come in contact with each other and fermentation should start. What happens if anaerobic conditions are not maintained during the process? So when sugar and enzyme combine, they form ethanol. During fermentation, ethanol is formed along with carbon dioxide. Ethanol, when combines with oxygen, which would happen if anaerobic conditions are not met, it would form ethanoic acid. This ethanoic acid, as you know, is a constituent of vinegar. So it would destroy the taste of wine. Moving on. Why is orthonitrophenol steam volatile while paranitrophenol is not? Steam volatile meaning low boiling point. That is why it's volatile. Low boiling point means weak intermolecular force. Weak intermolecular forces are there in case of orthonitrophenol because nitro group is orthosubstituted, it's in close proximity to the OH bond, and here there is a possibility of intramolecular hydrogen bond. Okay, so when intramolecular hydrogen bond is formed, now there is no possibility of intermolecular hydrogen bond. So the only interaction between these two compounds would be van der Waals forces, or maybe there's a possibility of dipole-dipole interaction, weak dipole-dipole interaction. But when we talk about para isomer, here since the OH is not in the close proximity of nitro group, there cannot be an intramolecular hydrogen bonding. That means there is a possibility for intermolecular hydrogen bonding. Intermolecular hydrogen bonding, strong, means there is a strong intramolecular force. So this means that these molecules are strongly held. That means you'll need to provide more heat to break them apart. Break this interaction apart, pull the compounds away or molecules away. So that means this will have higher boiling point. Simply because here the IMF, the intermolecular force, is hydrogen bonding, whereas there is no possibility of hydrogen bonding here because they have made intramolecular hydrogen bonding. Next question. Explain why bimolecular dehydration is not an appropriate method for preparation of ethyl methyl ether. Ethyl methyl ether is an asymmetrical ether. So let's see how dehydration of alcohol results in formation of ether. So what happens is, first when you treat it with acid, it gets protonated, the alcohol gets protonated. When that happens, another molecule of alcohol attacks this carbon. Why? Because after protonation, this oxygen becomes more electronegative because it has gained a positive charge, so it's going to pull the electrons, making this carbon partially positive. So making it very easy for these electrons on the oxygen of the other molecule to attack this carbon, acting as a nucleophile, right? And then water will escape, water will be released. And when this forms, the anion of the acid will grab the proton and it will ultimately result in formation of ether. This is the mechanism of acid dehydration in preparation of ether. Now this is all very nice for preparation of symmetrical ethers. But if you want to make an asymmetrical ether, you would think that let's say you have to make ethyl methyl ether. So you would say that, okay, let's take an methanol and ethanol. And in that case, you would not get the desired asymmetrical product. I mean, you would get it, but you would also get a lot of other products. Why? Because you would not be able to control what attacks what reacts with what. there is a possibility that methanol gets protonated and then another molecule of methanol acts as a nucleophile. Similarly, there is a possibility that ethanol gets protonated and another molecule of ethanol acts as a nucleophile. In those cases, you would get symmetrical ethers. Only when methanol gets protonated and ethanol acts as a nucleophile or vice versa, you will get an asymmetrical product which you desired. So this method is not appropriate because you would get a mixture of products. You would get a mixture of products because you would not be able to control which molecule gets protonated and which molecule gets to act as a nucleophile. Moving on. Ethers can be prepared by Williamson synthesis, in which alkyl halide is reacted with sodium alkoxide. Ditert butyl ether cannot be prepared by this method. Why? So this is the general reaction of Williamson synthesis. What happens is we take alkyl halide and we take sodium alkoxide, and then this will attack this. The mechanism would be SN2, okay, and you would get an ether, right? Now for this to occur, because the mechanism is SN2, we have to make sure that the Rx is least hindered. Okay, we learned in haloalkane and haloarenes that in SN2 reaction, SN2 mechanism occurs only when the alkyl halide is primary. That means least hindered, right? In that case only the reaction will go forward. But if you want to make ditert butyl ether, you would have to take both R as tert butyl, okay? But that would not happen because now this nucleophile is bulky nucleophile and it would not be able to attack this Rx because this is too hindered. It has bulky groups, so it would be too hindered and therefore the reaction will not proceed. So this will not occur. Now, let's say you have to make anisole. Okay, how would you proceed? What will you take as Rx and what will you take as RONA? Pause the video and think for a minute. Now, what you would take as Rx is this, okay, and you would also take sodium phenoxide. Why not the other way around? Because if you take alkyl phenyl halide or haloarene, it would not undergo SN2 reaction, or for that matter SN1 reaction, because haloarenes are very less susceptible to nucleophilic substitution. This we learned in haloalkanes and haloarenes. So we would have to take Rx as the aliphatic Rx, okay, and then this would attack this carbon and we would get the desired product. Moving on to the next reaction. Write the products of the reaction of HI with phenyl methyl ether. This is your phenyl methyl ether or anisole. When treated with excess of HI, what would we get? First, because this is an acid, protonation would happen, which would result in formation of iodide ion. Now, this iodide ion would generally attack least hindered R group. But in this case, when one of the R is a benzene ring, what would happen is this bond would never break. This bond would break. Why? Because as compared to the two bonds, this bond is stronger because it has partial double bond character. So this bond would break and you would get phenol and methyl iodide. Next question is, write the products of a reaction of HI with benzyl phenyl ether. So this is your benzyl phenyl ether. When it reacts with HI, it would get protonated first and will form iodide ion. Now, once it's protonated, generally the reaction in case of aliphatic Rs, the reaction takes place by SN2 mechanism. But here, the reaction would take place by SN1 mechanism because there is a possibility of formation of benzyl carbocation, which is extra stable. Okay, this benzyl carbocation is very, very stable. Therefore, the reaction would proceed through SN1 mechanism and phenol would be made and then iodide would attack here and benzyl iodide would also be made. Moving on to the next question. Very similar question. Here you have this compound. What would happen now? This would grab the proton the electrons would move to iodine atom, so iodide would be formed. Once the protonation happened, now think for a minute, which bond will break? Which carbocation would be more stable? We know that benzyl carbocation is stable because the positive charge gets delocalized over the benzene ring. And whenever in chemistry a charge gets to get delocalized over a number of atoms, that sort of stabilizes the system. Here, if this cation is formed, this carbocation is formed, the positive charge would get delocalized over two benzene rings. More delocalization, more stability. So this bond would break. And the carbocation that would be formed would be this, because it's more stable as compared to benzyl carbocation, because the positive charge would get delocalized over two benzene rings. So your products would be benzyl alcohol and diphenyl iodomethane. Moving on to the last question. What is denaturation of alcohol and why is it done? Now, commercially made alcohol, which is made because of its use as a solvent, that alcohol usually gets stolen. Okay, it gets misused. In order to prevent that, they make it unfit for drinking. They add some color by adding copper sulfate, and then they add some foul smell by adding pyridine. That tells the consumer that this is not for drinking. So this is how it's denatured. It would still serve as a solvent, but it would prevent the theft of the alcohol. So I hope this video made sense and I hope it helped you. So that's it for today. If this video helped you in any way, please like, share and subscribe. And God bless you. Best of luck for your exam.